Us back to the last afternoon post-lunch session for the application-driven coding workshop. Our speaker is Olgica Milenkovic.
That's not the title of the talk.
Indeed, I'm speaking to the first slide. We do have a lot of international women in the audience, so.
That's
you and Rudy really think alike. Thank you everyone for being here on International Women's Day on a Friday afternoon. And I hope you're not going to be bored and disappointed with wasting your time staying here, because I was hoping to start with some nice celebration of all women here and in the rest of the world. Even Google acknowledges the existence of Happy International Women's Day, although I couldn't really quite make out what is this supposed to be, but I saw a cat and I said, that summarizes it rather well. Women, pretty much international women across all the world, love cats, and that's enough for me. Google did a great job, fantastic. So, and now to something much more boring. Now we're going to talk about a problem that we just started working on. It's probably 6-7 months of intensive thinking. And in the spirit of this Simons Institute, where one of the most important names is obviously Dick Karps. We saw the board in the outside social area. A lot of the things I'm going to talk about ended up being NP hard. And it's a very difficult problem, but it's, in my opinion, also something incredibly practically relevant and also exciting mathematically. So the topic is data deduplication. And what is data deduplication? Data deduplication means when you and I and someone else who attended the same party wants to upload pictures on Facebook and we all have the same picture, maybe Facebook will try to save only one copy of that picture and not try to store all 3 replicas that were asked to be uploaded. So basically, we are interested in removing copies of the same data stored by different users. And why do we do this? Because we have such a vast amount of data. And without data deduplication, honestly, a lot of these systems wouldn't be able to cope with the volume of the data we have. And those of you that even think about the word deduplication would immediately think that's a form of compression. And some people have treated it as a form of compression. But what I'll do is I'll talk about problems in data deduplication that will lead to some interesting questions regarding how the files are going to be retrieved after deduplication. And just to give you a little bit of a background on data deduplication, usually it's performed in 2 manners: inline deduplication and post-processing deduplication. Post-processing deduplication is a method of deduplicating or removing redundant data by collecting the data, storing it, and then, as the word says, post-processing, removing redundant pieces of data from what's already stored. While inline deduplication really means you're trying to remove the redundant pieces of information while you're in memory, before you store the data on a hard drive or a storage system. And some companies openly admit that they're doing deduplication. So if you look at the NTFS file, the new technology file system developed by Microsoft, they will make it very explicit. They say, we use deduplication. Others, like Dropbox, have resisted admitting, but here what I wrote down is basically what hackers online say how to test and how to check if deduplication is done in Dropbox. And I won't talk about hashing and other approaches that are used for deduplication purposes, but one way to tell for sure that some deduplication process is ongoing is to check how much time does it take for your file to be stored. So you don't even have to be a hacker to figure that out. So let me try to explain, and it's a very simple approach, how inline deduplication works. So the only point here is that you don't store the file immediately. You process the file as it as it arrives into the in-memory part of your system. And before you archive or store it, you need to do a few steps. So the file comes in, and the first thing you will do is you will break the file into pieces that are called data chunks. A lot of you know what data chunks are. So let's say in this case, the file came in, and it has 3 data chunks, 1, 2, 3. Then you're going to look at which chunks are unique, meaning the word unique is used in this context. It means the first time you saw them. So I saw 1, 2, 3 for the first time. I'm going to put it in what is called a chunk store, or a storage system for chunk. Then the second file comes in, and then you notice that the chunk 1 already appeared. So the only new unique chunks are 4 and 5. You will deduplicate 1. And now you have 4 and 5. You will add 4 and 5 to the store. Then you have 3, 6, 2. In this case, you saw both 3 and 2, but you didn't see 6. So you will declare 6 a unique chunk. You will do, let's say here, 7, 5. You will realize that 7 is a unique chunk. And if I summarize them here, what you kept doing is you kept adding the unique chunks into a chunk store one after another after you removed everything that was redundant. And what do you get as a mathematician when you see this? What you really get after this process is a permutation of the chunks. In this case, the permutation of the chunks is such that I didn't break up the order of the unique chunks in each file. But in principle, you can do that with deduplication post-processing. The next thing you need to do is you need to add pointers, because if I had my file 362, you need to tell me where am I going to retrieve the file, the data chunks from. And then you add labels that say there was your chunk 3, there was your chunk 1, and then there was your chunk 2. Or if they're adjacent, because they were in the first file, then you just add 2 labels, 3 and 1, to indicate this was the third and first chunk, and then the second chunk was there. And notice something very important here. The way I did the duplication in this process, my 2 chunks for this file are here, and then the third chunk is far, far away from the first 2 chunks. And that is called fragmentation. And that is going to be the topic that I want to discuss today. The issue of fragmentation, which is real, bothersome, discussed in many conferences in computer engineering. I will cite some papers from the Usenix conference. It's really creating a lot of trouble. And why is it creating a lot of trouble? I'll discuss it in a second. Before I say talk about fragmentation in more detail, I also want to mention that when you have post-processing deduplication, you are allowed to, you retain the unique chunks, but then you can break them up. What that means, I can split 1, 2, 3. They don't have to be kept adjacent. I can split 4 and 5, and I can put them in a different order. So I can take an arbitrary permutation of these chunks. And in this case, for example, if I put them in an arbitrary order, this is not a good order, then for 3, 6, 2, I really split the chunks far apart from each other. I have to look at 3 different regions in the chunk store in order to recover the original file. And how do people really deal with this fragmentation issue? There are many, many papers written about how do you get the original file back when you have this fragmentation problem. And most papers discuss this retrieval approach. They say just retrieve the whole segment of data chunks such that you cover all the chunks that you need. So if my file was 362, I will read everything in the chunk store in a way that I get 362. What that means is I'll need to read a much longer block of consecutive chunks. In this case, 60% more of a reading frame. And then I have to do post-processing. So I would read 2, 3, 4, 5, 6, and then I would say, obviously, I can't give this whole fragment to someone who only stored 362 for privacy issues. I would have to parse out 4, and I would have to parse out 5. And that is, again, a very problematic issue, because you have to get rid of a bunch of data chunks. You read a lot, and then you get rid of it. It's almost a case for compressive sensing. And the other thing that is very problematic in data deduplication is the fact that you cannot rely on keeping just one replica of your chunk, because when you have a chunk that appears many times, it's very relevant for the users. You need to keep that chunk at least with several copies. And that is another thing that computer engineers are quite interested in. And I had a colleague who was actively working in this area, and they usually develop rules of thumb. And they say you need to do some kind of counting, how many times a population of users wants to store a chunk. Then you do the count. And in this case, for example, you see chunk 1 was quite popular. 3 users out of 4 stored that chunk. So it makes sense to keep chunks that are in high demand stored multiple times. You're not going to just use one replica of each chunk. And what you do is, in this case, you can add an extra copy of chunk 1 somewhere in the store. And for convenience, I added it at the end, but you could have added it in some other location. And that is an extra copy. And the rule of thumb that computer engineers tell you is good to use in practice is go with roughly log m duplicates of the chunk that you're count. So if a chunk is stored, let's say, 100 times, have at least 10 copies of that chunk. Don't deduplicate it to the bare single permutation level. So what has been done about studying these problems in a more mathematical way? I kept talking about computer engineers are extremely interested in these problems. So if you want to check the computer engineering literature, the work has been ongoing for many, many years because we had a data revolution and explosion in this century. And one of the papers, my favorite papers in this area, is a Usenix paper that talks about the dilemma between deduplication and locality. So if you see the word locality, it really refers to fragmentation, because you want to keep the chunks locally close for each file, but it's impossible. It's a tension, because some file may have it in a different order, another file may have it in a different order, or some files may have only, or users may have only a subset of chunks, and so on. And on the coding theoretic aspects of deduplication, there was really just a handful of papers in this area. With Salim, long time ago, we started looking at deduplication in the context of distributed storage. And we really didn't think much of it, but at that time, the only thing we were concerned about is, oh, you have a distributed storage system, and then maybe there is a tension between the redundancy in the distributed storage codes and the deduplication process. How do you update the files if someone wants to store a redundant copy of something that was already there? But it was published in a non-information theoretic venue, and a lot of people don't know about that work. But then Neeson published a paper in the IT, and it was in 2019, and it took really a compression approach, an approach to the problem that deals exclusively with the idea of how do you model a file, how do you model the process of deduplication itself, but there was absolutely no mentioning of the issues of fragmentation and locality, basically. And then my former student, Farzad, and his student started working on data duplication, but again, not from the perspective of trying to analyze and study locality, but more from the perspective of, oh, what if you have non-exact copies of the same file, which is an important topic. So what if someone took an image just a second later than someone else? The image is almost identical, but there are some tiny differences. Again, nothing about fragmentation. So what I want to do today is try to talk about the issue of locality, the issue of fragmentation. And I'm going to ask a very silly question. Can redundancy help with fragmentation? And when we started talking about this problem, we said, come on, we are trying to do deduplication, and now we want to add redundancy. But it makes a lot of sense to ask this question, because we know that's what we do with joint source channel coding. We remove some type of redundancy, and then we add good redundancy for error correction. So let's deduplicate, and then see if we can add some redundant chunks so that we take care of the issue of file fragmentation. And obviously, how would you do that unless you have some good models that you can potentially analyze and get some interesting results for? So how am I going to model the creation of files? So we thought a lot about it, and we thought that the approach proposed by Neeson wasn't the one that we would like to use for fragmentation purposes. So we thought that it would make sense to model the way the files are created using a graph. So the graph will have a vertex set where we have n data chunks serving as the vertices in the graph. So each chunk is going to have its own vertex, and the edges will tell you which chunks could be adjacent in a file. So in that case, the set of all self-avoiding walks on such a graph of length less than or equal to t, so this puts a bound on the length of the file, will be the set of all files that we allow. And why does that make sense? The chunks have some kind of logical connections between them. It makes sense to model them as graphs, and the logical connections are explained through edges in the graph. And a path is basically what will define a file, and we're assuming that the files are not longer than length t. And why self-avoiding walk? For simplicity, we will assume that all of us clean our own data before we send it to Dropbox, which is not really true. I have at least 10 copies of every file somewhere in Dropbox. But self-avoiding means let's not assume that a user themselves has the multiple replicas of the same data chunk. So here is, for example, a file graph, as we call it in this talk. And here is an edge from 3 to 5. The graph is undirected. And I am saying that this is a file of length 2 chunks, but it's really one step in the graph. So I will use the parameter t to tell you how long is the walk on the graph. And in this case, it's exactly one step. So t is equal to 1. But with this t is equal to 1, I'm getting 2 chunks. And I'm getting 3 and 5. And the order does not matter. It's 3, 5 as a set, for the simple reason that you remember when I explained to you when the duplication is done, because you have to point to the various locations where the different data chunks are, you add pointers telling you what chunk order did you have, or sometimes the chunks themselves have headers that tell what order they should come in for a specific user. Here is another file. This would be another file. This time the file has 4 chunks, and it's a self-avoiding walk of length 3 on this graph. And again, I'm just writing it as a set of chunks that correspond to this file. And I will use, as I mentioned, W with the subscript T, which tells me how large the maximum file size can be, to denote the set of all possible, basically, walks of length less than or equal to t on the graph, which are going to mimic or represent the files, the files that I'm working with. So, yes?
The assumption that in a file, chunk cannot be repeated. Is that an assumption?
That is the assumption. If it's my file, I should be doing good housekeeping. And it's not something that is necessary for any of the derivations I will go through, but it causes confusions with some of the definitions. And you will see that in a second. But it's something done more for convenience. The assumption is if I have a file, I'll remove my redundant chunks before I put them on Dropbox, let's say. Okay? So what is then a chunk store? Let me go back. I think I pressed it. A chunk store, I already mentioned it. It's this linear order of the chunks that are presented to the system, either in a online or in a post-processing manner. And what we will discuss is two cases where the chunk store sequence is nothing else than just a permutation of the unique chunks of all the files we got. And we're going to discuss the case where the chunk store can have redundant copies of chunks for the purpose of reducing fragmentation. So, oops, I'm pressing this too hard. So for example, in this case, I have 5 nodes, and a chunk store example could be 1, 2, 3, 4, 5. It tells me in which order I'm storing these chunks. And then this is a redundant chunk store because I have 3 copies of chunk 1. And that is a bad idea. Again, look, this chunk is a bit isolated, but I'm just giving you a few examples in terms of what we will call a chunk store. So we are first going to talk about chunk stores where we have exactly n, which is the number of unique chunks capacity, and then we are going to talk about the redundant chunk store case. So this is the chunk store model. Let me skip it. So we decided what we're going to use as a model for the files and the chunks. Now I need to tell you, what is my criteria for fragmentation? How do I measure the level or the expansion caused by fragmentation? So again, this is the file I want to read. And look, I have to get this file, I have to read this whole block. So it makes sense to measure how poorly are we doing or how badly are we doing with fragmentation by looking at the length of the whole block that I need to retrieve of chunks, divided, scaled by the total length of the file as a measure of how much I expanded the file. Because here I would have 3 blocks and I will have to read 1, 2, 3, 4, 5 blocks. And the chunks obviously don't even have to be of the same size. But in this case, I'm just counting how many chunks. It would be much more complicated to even take into account the sizes of the chunks. And the fragmentation expansion for a file W for a given chunk store S will be equal to the min SWS, which is the length of the shortest substring of S that contains all chunks in W, scaled by the length of the original file, not the redundant block of chunks that you have to read. So this is going to be a value greater than 1, because this is the number of chunks you really had, and this is the number of chunks you have to retrieve and then post-process by removing the chunks that are not necessary. And this is going to be a number, as I mentioned, larger than 1. So for example, if I want 362, I need to read 2, 3, 4, 5, 6 and remove the chunks 5 and 4, and I am not doing a good job if I'm spreading the chunks out too much. So my chunk optimization criteria or chunk placement optimization criteria will be this. This FTG is nothing more than a minimum over all permutations of in the symmetric group Sn over all n chunks, unique chunks. And then I will try to minimize the maximum spread for any file generated by that graph model that I have. So this is going to be over all files that are of length less than or equal to t of this ratio here. And this is the most commonly used metric. Another metric that you can use, which is also very commonly used, is take the average in some sense of all the expansions or fragmentation expansions of all files, and then try to minimize that. And then there are some other interesting things that certain systems may use where you don't want to go through the post-processing step where you have to remove chunks, clean everything up, where you make jumps. That is also not a cheap thing to do in storage systems, but let's say I just do 2, 3, and then I jump to 6. In that case, the metric could be the number of jumps that you make to retrieve the file. And again, I have no time to discuss any of these, and I'm really running late here. And then the third or fourth criteria could be the one thing that is also very, very practical is don't break up unique chunks, their orders, because if they came in a file in a certain order, do not split them and reshuffle them. Try to keep them in the same order, because that will that is good from the perspective of write time. But it may hurt you, obviously, because you're looking at the restriction of the set of possible permutations of the file chunks that you have. So Houston, we have a problem. And the problem is very obvious. If you know graph theory and you know hard problems in graph theory, the moment you see a min-max, you're kind of grilled. And we knew this is going to happen. And we thought, okay, it's worth studying it because that's the natural formulation for the problem. And the computer engineers really didn't realize that it's hard. They knew empirically it's very hard, but they never formulated it this way. And problems that those of you that are computer science oriented will recognize showing up in my definitions basically are the graph bandwidth problem, the graph edge sum, so on and so on. And there's a beautiful review. I love reading some older theoretical computer science paper, a survey of solved problems. That's an overstatement. It's not solved. They're all NP hard, pretty much. So, and what I'll talk about is the graph bandwidth problem, because that was the formulation that is the most common one. You retrieve the substring of the chunk store that is of shortest length and covers all the chunks in a file, and then you try to find this minimum coverage length for each files. They're normalized with their length, and then you try to find a placement of the chunks that minimizes that maximum spread. So that for t is equal to 1, when I have only one edge, when my file contains only 2 data chunks, that problem actually is equivalent to the graph bandwidth problem. And the graph bandwidth problem has been studied since the 60s. So what does the graph bandwidth problem say? Given a connected graph G, find the optimal ordering of vertices in V, and ordering means permutation, such that the worst stretch, that's what they call it, stretch, bandwidth, of an edge is minimized. This is it. That's exactly what we're looking at, and we are being even more greedy. We want to minimize the stretch of files of length less than or equal to t. So even if I have t is equal to 1 edge, it reduces to the famous graph bandwidth problem, and I can show easily that for any arbitrary file size upper bound length ft, this fragmentation expansion will be sandwiched very tightly around the bandwidth. So it's half the bandwidth as a lower bound and the bandwidth as an upper bound. So that is not good. And then we said, okay, we are engineers. We are not mathematicians. We shouldn't give up, because not every graph is a good explanation for file models. And we said there must be obviously some graphs for which it's not hard, and those graphs can be good for modeling file systems. And what we saw, it remains hard for pretty much everything. Trees, caterpillar trees, I'll explain what a caterpillar tree is, and many other cases. So for example, what is a caterpillar tree? It's a tree where the maximum degree of any node can be, yes, please.
The question, is it also NP hard to approximate?
Yes. Depends. I'll go over some graphs. You will see. We'll focus on bounds. I don't know how much time I have. I want to talk about the redundant part as well. But here's a caterpillar, and it's a nice motivation for what we want to do, because this is still pretty hard. But we know about approximation algorithms and approximation guarantees and efficient algorithms. And it couldn't be simpler than this. There is an approximation algorithm within a factor of log n over log n, such that, and that algorithm is super efficient. All it says is bend the hairs of the caterpillar, and then go through a zigzag order. So I bend this here, and then I would read it as 1, 2, 3, 4, 5, 6, 7. Then I bend this guy. I can bend it either to the left or to the right. And then I just go and read them in a zigzag order. What that means, this way, this way, this way, this way, this way. If I bend it this way, this way. So it's a very straightforward algorithm. But unfortunately, caterpillars are no good when it comes to modeling files. I mean, what kind of file system would look like this? But it gave us a good idea. And I'll hopefully get to that idea at some point. So then we said, okay, let's look at bounds. Let's see, can we learn something from the bounds themselves for the bandwidth graph bandwidth problem that will indicate what we are supposed to do? And there are some really straightforward bounds. For example, an upper bound that says that the bandwidth is less than or equal to n minus the diameter of the graph. That is very important for a lot of the analysis we did later, because the diameter of if the diameter is large, the bandwidth will be small. Why? Because a large diameter means the chunks are already naturally in the graph, not very nicely connected, so it shouldn't be too hard to find a linear ordering so that you don't expand too much. So this bound is horrible, especially for cycles, but it gives you a good idea. Increase the diameter of the graph, you will decrease the bandwidth, at least as an upper bound. Then you have special graphs like square grids. Again, doesn't look like a good model. And then you have really beautiful lower bounds. These are probably the best bounds out there, and I had to mention them. We're not going to talk much about lower bounds, but this is a beautiful work by Fan Chung and Seymour. I'm a big fan of both of their works, and I can discuss this so-called local density bound offline. So we said, okay, we have a lot of problems here. How are we even going to analyze this problem when everything seems to be hard? And Yun Han, who I didn't mention, and I should have at the very beginning because I was too obsessed with cats and whatnot, Yun Han is a very, very smart guy. And he was not giving up. And he said, I'll find something that works. And he says, okay, a cycle. Oh, okay, boring file system. But okay, let's look at the cycle. Well studied. What you do is well studied from the perspective of bandwidth problems. What you do is you fold the cycle, you flatten it, so you get something like a pancake, and you do that zigzag. I keep bringing up that zigzag idea. I mentioned it in the context of the caterpillar, and in the context of a cycle, you squish it, and then you do zigzagging, 1, 5, 2, 4, and 3. And this is what you get, and the expansion, or the bandwidth, is 2, meaning you need to read twice as many chunks in order to recover, in the worst case, whatever file you're after. So this is, and I'm happy that I'm going a little bit faster, sorry for that. Then we thought, okay, cycles don't make sense as models for file systems, but what about some graphs like this? And we did a due diligence of checking the literature on bandwidth problems. What about graphs that look like a bunch of cycles that are stacked on top of a Hamiltonian path? And we call them sparse Hamiltonian path graphs. Why is this a good model for a file system? Because I think it is a good model. And the insight you can get from these graphs is actually very, very useful. And the reason is that there is a natural ordering of chunks in a line. If you think about movies, for example, a bunch of the chunks in close to each other in this linear order could be chunks that correspond to horror movie 1, horror movie 2, horror movie 3. And then you switch from horror movies, let's say, to whatever, romantic movies and whatnot. But then at some point you get bored storing and watching one type of movie. You move, you have these arcs, we call them rainbow arcs, that transfer you, let's say, from the world of horror movies, you're sick and tired of them, to another genre. And that is actually a very simple yet pretty realistic model, as realistic as a model can be with the disclaimer, for how the files could be formed. And we started looking at, did anyone look at these graphs? Because we really wanted to have a good mathematical problem and a formulation. And it turns out these are not caterpillars, these are not trees, these are very unusual types of graphs that people in the theoretical computer science community were not that interested in. And what we did is, I'll go very quickly over this, we came up with, I think, a very, very interesting algorithm and a very interesting idea that generalizes the notion of folding that I described in the context of the cycle. And that algorithm is super complicated, and it gives you a bound that says the number of times you're allowed to jump from one movie genre to another, the number of red arcs that I see here, is going to give me an upper bound on the fragmentation level for any value of t, which is of the form 9k/5, slightly less than 2. So if you're searching or storing files that follow this kind of generation pattern as self-avoiding walks on these graphs, you will have to retrieve always close to twice as many data chunks and get rid of them. And the proof is actually really nice. The proof, this is a vegan sandwich. This is a picture of a vegan sandwich from a New York deli. And it's folding. You remember it's folding. But now you have to fold multiple arcs with intersecting, that intersect each other. And the really beautiful idea that Yoon Han and Jin Sima, who is a postdoc in the group, had was, you know, let's fold these things that look as cycles but have intersections. Let's try to fold them like we did with the cycle case, but now let's try to fold different pieces of those cycles in such a way that align what we call the feet of those cycles. So the feet would be aligned this direction. It really looks like a folding that includes multiple layers of a vegan deli sandwich. And the proof for this is rather complicated. I can share some ideas behind it, except this folding part. The upper bound of 2K is kind of natural and very easy to prove. We had to work really hard to go from 2 to 9K over 5. Oops. So now, unfortunately, I don't have that much time. But now the question is, can redundancy help? So far, I was looking at the problem where I'm trying to arrange the chunks so that I don't stretch out the reading frame too much to retrieve any file that can be modeled as a walk in a graph. But can redundancy help? And the answer is rather obvious if you look at the example of a cycle. I already mentioned when you have a cycle and no redundancy, the bandwidth and hence even the FT, that's easy to show, the stretch for the deduplication problem, fragmentation problem is 2. What is the issue here? I have 1, 5, 2, 4, 3. I have an edge between 1 and 5. I have an edge between 2 and 5. But the problem is that there are some edges that are not adjacent in this ordering. But what can I do then? Oops, sorry. What I can do is, I can add one redundant vertex. And that's a no-brainer. What am I really doing? I'm cutting an edge between 1 and 5, and I'm adding a replica of 1 at the beginning, at the end. That's it. And then I'm linearizing. I'm really linearizing that cycle. So I'm going with 1 extra stored chunk in this case. I'm going from 2, from a bandwidth of 2 to a bandwidth of 1. And that is really neat, but it's for a single cycle. Again, not an interesting file system problem. And it's not the simple idea that you take the optimal way in which you order the chunks when you have no redundancy. In this case, I would use the zigzag. But when I am allowed to add redundancy, then I cannot just add some extra symbol within the zigzag order. That's not going to work. You have to start from scratch. And how much time do we have? Assuming 3 minutes? Oh, 5. Okay, 5 minutes. Great. So how do we deal with this problem? What I'm really asking is something that I haven't seen at all in the theoretical computer science community. How do I add nodes to a graph in such a way, redundant copies of the nodes, that I preserve the paths of length less than or equal to t. My files have to be preserved. I add extra nodes so that I can actually reduce the bandwidth of the graph. And I'll skip this. So there are a lot of relationships to graph factorization. And I'll take this offline because I want to go back and show you a work of my former advisor from 2003 that got so little attention that my heart is breaking. Because when Yoon Han and Jin were telling me about their attempts, and I said, I know this somehow, this looks really familiar. And then I remember Sean Coffey, who was a professor at University of Michigan, worked on a problem and published a paper in the IT in 2003 called Fundamental Limits for Information Retrieval. And then Sean Coffey went to industry, became, from what I heard, very wealthy. But I love this problem, and I used to love it as a student, and I can't believe I forgot it. So I want to tell you about this problem because this is exactly the kind of problem that we were discussing, but for a grid graph. So what Sean Coffey was asking is not exactly the same kind of question we had, but it was very related in a sense that you can get a lot of really good ideas that can help with his problem, help with our problem, and vice versa, go back to his. So what he was looking at, and Matt Klimesh, was the following. If you have a two-dimensional structure, a 2D grid, every vertex, let's assume it's a torus, every vertex has 4 neighbors at distance 1. This would be distance 1. And now you want to take a two-dimensional structure and put it on a line so that you preserve the local neighborhoods. And as information theorists, you have seen these problems before, and that's what this paper was all about. You have, for example, here 4 neighbors at nearest neighbor at distance 1. Here you have only 2. So something has to give because you cannot preserve the local neighborhoods. And Sean Coffey and Matt Klimesh were interested in this problem insofar that they wanted to find the best way to scan the graph, the grid graph, so raster scan or some other type of scan, to convert the graph into a line so that the local neighborhoods are as preserved, as close to each other as possible. One thing that you should be thinking about is there was this beautiful work by Lempel and Ziv, where they said, how do you compress images? You know that there is a lot of correlation between the pixel colors and intensities when the pixels are close to each other. And if I want to do a compression, run a compression algorithm, which exploits that similarity, exploits the correlations between adjacent pixels in an image, they propose to linearize the image. And I don't know if you remember what they did. They used a special scan for the image to convert it into a one-dimensional structure. They used something, but it wasn't a raster scan, and the raster scan is not the best one to do to preserve the neighborhood structure of a 2D grid on a 1D plane, 1D line. It wasn't the raster scan, and it wasn't the Hilbert scan. If you think of Hilbert or Hilbert-Peano space filling curves, that's what Lempel and Ziv did, from what I remember. But that's not the best way to scan a two-dimensional grid into a one-dimensional vector or order in order to maintain as much as possible the neighborhoods in a 2D structure on a 1D string. So the best thing, and I remember that I found that paper, I read that paper because I was acknowledged in the paper saying, thank you to Olgica Milenkovic for telling us about this scan, the famous Mitchinson and Darbin scan from 1986. The raster scan, if you go you go in a raster scan format for a grid, you will get roughly 0.5 n as the average distance between the 4 neighboring points. Why? Because if I have these 4 neighbors here, each one of them is a distance 1. But if I put them in a raster scan on a line, then these 2 will be at distance n, and these 2 will be at the distance n. And I'm dividing by 4. I don't count the +1. So I'll get roughly half an n of an average distance between the neighbors in the 2 grid when projected on a one-dimensional grid. But Mitchinson and Darbin managed to go down to 0.434. And it's a beautiful scan. It basically says use a raster from both ends, and then when you're in the middle, you do something totally different. It's a very interesting paper. So I thought to bring it up. And 20 years ago, Sean Coffey asked the same thing. He says, does it make sense to add redundancy so that you preserve the 2D neighborhoods better when you project everything on a one-dimensional line? 20 years ago, and he had a beautiful approach. So all I'm going to do is show you how his approach worked. So what he did is he said, break the grid into subgrids, and then make the subgrids, pieces of the subgrid such that you take overlapping squares. So just to make clear how it works, this is the grid of points or pixels. And now I take a subgrid, this subgrid, the red one, and then I take an overlapping subgrid. So these are going to be repeated. These points are going, or pixels are going to be repeated twice. These pixels here are going to be repeated twice. And then you do it in a recursive way. And then you stack the enlarged subgrids into a bigger grid. Oops. You stack it into a bigger grid, and then yet another bigger grid. And then you run a raster scan because they didn't want to bother with the Mitchinson-Darby thing. So what you get is you started with the smaller grid, but you took subgrids that overlap. Basically, you have redundancy. You stack those subgrids together, and then you use a raster scan. But every time you go through one block in the raster scan, you go one level deeper until you reach the lowest level, and there you do an ordinary raster scan. So you have a lot of redundancy. And I'm running out of time, I know. This is the result from their paper. It really corresponds to infinite walks on a grid graph. And what I want to say is this motivated us basically to come up with a very similar approach. We are going to enlarge the neighborhoods of nodes in our graphs by cutting an edge and repeating closest neighbors. That is exactly the kind of idea Sean Coffey and Matthew Klimesh had, and we are going to do it in a recursive fashion. And for example, this is the best way to explain it. I'll take these two nodes, I will cut them into two pieces, create two copies of that node, and then I'll do this node, I'll cut it into two pieces. I reduce the bandwidth from 3 to 2. I added 2 redundant nodes. What am I really doing? I'm increasing the diameter of the graph. That's what also happens with Klimesh and Coffey, because when they keep replicating things in these blocks, they kept increasing the distances between neighbors. They were making the graph less connected. So I'll skip all this and the results, and I'll tell you a bunch of open problems. We would still love to know more about the different types of fragmentation metrics that are out there and how to analyze them. There is the famous edge sum problem that I didn't have time to talk about. How much can redundancy really help? We have some specific examples based on the ideas that either came from our own musing about the problem or from Matthew Klimesh and Sean Coffey's paper. And the most interesting thing, which seems to indicate that this may be actually something that is potentially practical, is the fact that the redundant nodes that you keep adding to make your linear store less fragmented seem to be the nodes that are very central to the graph, which means a lot of paths are passing through them. Those you would have to duplicate anyhow, because those are the ones that are frequently accessed, and you want to keep them in order to prevent failure and loss of information. And there are many, many other questions if anyone is interested in. I will be happy to discuss it. And here are some of my favorite references from theoretical computer science. And with this, thank you very much. And I'm sorry I went over time.
Thank you. Questions?
Are you allowed to make exclusive OR of chunks?
Oh, that's a good question. We didn't think of it. Oh, bummer. As a coding theorist, now I feel embarrassed. I don't know. That goes back to the stuff we did with distributed storage. I'm really not using my old papers properly. Maybe. That's a very good point. We didn't think of it. Because in that case, it would make sense to retrieve them on the line. That's a very good question. Thank you so much. We didn't think of it.
So
yes.
This problem of mapping the square to the line was very intriguing. So like a continuous version of it, right? I mean, is there like a continuous mapping from R2 to R1? I don't think there is any. So
no, I mean, it's actually really intriguing. That's why I'm so upset that that paper has only 3 citations. I thought it was a very interesting question, and it's very relevant for compression, for other problems that have nothing to do with deduplication. But I know that it was used, that the raster scan problem, the scanning problem to preserve 2D, 3D, and sorry, I'm all over the place. Coffey's paper actually had it for a D-dimensional grid. So I really warmly recommend checking that paper out. Theirs is a Markov chain model. I could not squeeze all of this. We are just starting to explore all sorts of
I was
dimensions.
wondering if I know, like a continuous version of it, can't tell us anything.
No, but you can make the grid finer, you can increase the dimension, you can make the steps have different probabilities, which would make sense as well. You can make all of this, and this is the next thing we will try. I forgot to mention it. This is a very hard problem because it's combinatorial. But if you treat it as a Markov chain with certain transition probabilities, and that's what Coffey really did, he modeled the file system as a random walk on a graph, even in this case, a d-dimensional grid graph. And then the question was, how much are you losing in locality when you go from 2D to 1D, 3D, and 2D to 1D? So these are all very natural questions studied by CS people before. But the redundancy, Sean Coffey was the first one to do it.
So if I understood Mina's talk correctly, it was all about trying to have data in such a way that you have many servers you can get it and get large bandwidth, right?
Mm-hmm.
If I understand your talk correctly, if you succeeded, you would have everything together, almost guaranteeing that you have, in that sense, the worst solution. So you want to fight it out? Which
It's International Women's Day. I don't fight with women on this day, but my bandwidth and Amina's bandwidth, I don't think are the same bandwidth. The word is there and the conflict may be there, but
I think no conflict. One is for hard drives. Which you remember defrag in your laptop 20 years ago, maybe? They would do yeah.
Oh yes, that's true. Defrag, yes.
But this is not on your hard drive. This is for storage system, right? Otherwise, deduplication is not for your own thing. It's
No.
But it's the same principle. It's the same principle.
Locality.
Yeah, you want locality, right? You don't want fragmentation.
Dedup is for archival storage, so it's rarely.
Exactly. When you want to access, you need redundancy. If you want to archive, you want to.
Yeah. Because you would have a dual problem of spreading, having more locations, so you bandwidth.
Exactly.
But I think it's a little more like somebody mentioned the joint source channel before. You want to take out all the deduplicate and then provide the right redundancy for the network. They might be mismatched. So you might want to do.
So it's the problem is kind of really a nightmare, but it's really interesting. I think if you know how to solve something like this with redundancy, and I loved Simpo's idea, never trust my mind, with coding redundancy, not simple repetition redundancy, then it could be very interesting for practical implementations. I think even the fact that you know that it's so problematic for simple file models like we called it the rainbow graph, the Hamiltonian path with a bunch of sparse arcs added to it is. And it's a big practical problem in computer engineering.
So I should do coded deduplication, I guess.
Yeah, we would. Okay, sorry. Yeah.